An electronic amplifier, amplifier, or amp is an electronic device that increases the power of a signal. It does this by taking energy from a power supply and controlling the output to match the input signal shape but with a larger amplitude. In this sense, an amplifier modulates the output of the power supply. There are four basic types of electronic amplifier: the voltage amplifier, the current amplifier, the transconductance amplifier, and the transresistance amplifier. A further distinction is whether the output is a linear or nonlinear representation of the input. Amplifiers can also be categorized by their physical placement in the signal chain. Figures of merit. Amplifier quality is characterized by a list of specifications that includes gain, the ratio between the magnitude of output and input signals; bandwidth, the width of the useful frequency range; efficiency, the ratio between the power of the output and total power consumption; linearity, the degree of proportionality between input and output; noise, a measure of undesired noise mixed into the output; output dynamic range, the ratio of the largest and the smallest useful output levels; slew rate, the maximum rate of change of the output; rise time, settling time, ringing and overshoot that characterize the step response; stability, the ability to avoid self-oscillation. Amplifier types. Amplifiers are described according to their input and output properties. They exhibit the property of gain, or multiplication factor that relates the magnitude of the output signal to the input signal. The gain may be specified as the ratio of output voltage to input voltage, output power to input power, or some combination of current, voltage, and power. In many cases, with input and output in the same unit, gain is unitless. The four basic types of amplifiers are as follows. Voltage amplifier. This is the most common type of amplifier. An input voltage is amplified to a larger output voltage. The amplifier's input's impedance is high and the output's impedance is low. Current amplifier. This amplifier changes an input current to a larger output current. The amplifier's input impedance is low and the output's impedance is high. Transconductance amplifier. This amplifier responds to a changing input voltage by delivering a related changing output current. Transresistance amplifier. This amplifier responds to a changing input current by delivering a related changing output voltage. Other names for the device are transimpedance amplifier and current-to-voltage converter. In practice, the power gain of an amplifier will depend on the source and load impedances used as well as the inherent voltage current gain. While an Ef amplifier may have its impedances optimized for power transfer, audio and instrumentation amplifiers are normally designed with their input and outputs impedances optimized for least loading and highest signal integrity. An amplifier that is said to have a gain of 20 dB might have a voltage gain of 10 times and an available power gain of much more than 20 dB, yet actually be delivering a much lower power gain if, for example, the input is from a 600 ohm microphone and the output is connected to a 47 kΩ input socket for a power amplifier. In most cases, an amplifier will be linear. That is, the gain is constant for any normal level of input and output signal. If the gain is not linear, for example, clipping of the signal, the output signal will be distorted. There are however cases where variable gain is useful. Exponential gain amplifiers are used in certain signal processing applications. There are many differing types of electronic amplifiers used in areas such as radio and television transmitters and receivers, high-fidelity stereo equipment, microcomputers and other digital equipment, and guitar and other instrument amplifiers. The essential components include active devices, such as vacuum tubes or transistors. A brief introduction to the many types of electronic amplifiers follows. Power amplifier. The term power amplifier is a relative term with respect to the amount of power delivered to the load and/or provided by the power supply circuit. In general, the power amplifier is the last amplifier or actual circuit in a signal chain and is the amplifier's stage that requires attention to power efficiency. Efficiency considerations led to the various classes of power amplifier based on the biasing of the output transistors or tubes. See power amplifier classes. Power amplifiers by application. Audio power amplifiers. RF power amplifier, such as for transmitter final stages. Servo motor controllers, where linearity is not important. Piezoelectric audio amplifier includes a DC to DC converter to generate the high voltage output required to drive piezoelectric speakers. Power amplifier circuits. Power amplifier circuits include the following types: vacuum tube valve, hybrid or transistor power amplifiers, push-pull output or single-ended output stages, vacuum tube amplifiers. According to Simmons, while semiconductor amplifiers have largely displaced valve amplifiers for low-power applications, valve amplifiers are much more cost-effective in high-power applications such as radar, countermeasures equipment, or communications equipment. Many microwave amplifiers especially designed valves, such as the klystron, gyrotron, traveling wave tube, and crossed-field amplifier, and these microwave valves provide much greater single-device power output at microwave frequencies than solid-state devices. Valves tube amplifiers also have niche uses in other areas, such as electric guitar amplification, in Russian military aircraft, for their EM tolerance, niche audio for their sound qualities, transistor amplifiers. The essential role of this active element is to magnify an input signal to yield a significantly larger output signal. The amount of magnification is determined by the external circuit design as well as the active device. Many common active devices in transistor amplifiers are bipolar junction transistors and metal oxide semiconductor field effect transistors. Applications are numerous. Some common examples are audio amplifiers in a home stereo or PA system, RF high power generation for semiconductor equipment, to RF and microwave applications such as radio transmitters. Transistor-based amplifier can be realized using various configurations. For example, with a bipolar junction transistor we can realize common base, common collector or common emitter amplifier. Using an MOSFET we can realize common gate, common source or common drain amplifier. Each configuration has different characteristic. Operational amplifiers. An operational amplifier is an amplifier circuit with very high open-loop gain and differential inputs that employs external feedback to control its transfer function, or gain. Though the term today commonly applies to integrated circuits, the original operational amplifier design used valves. Fully differential amplifiers. A fully differential amplifier is a solid-state integrated circuit amplifier that uses external feedback to control its transfer function or gain. It is similar to the operational amplifier, but also has differential output pins. These are usually constructed using BJTs or FETs. Video amplifiers. These deal with video signals and have varying bandwidths depending on whether the video signal is for SDTV, EDTV, HDTV 720p or 1080p etc. The specification of the bandwidth itself depends on what kind of filter is used Euro, and at which point the bandwidth is measured. Certain requirements for step response and overshoot are necessary for an acceptable TV image. Oscilloscope vertical amplifiers. These deal with video signals that drive an oscilloscope display tube, and can have bandwidths of about 500 MHz. The specifications on step response, rise time, overshoot, and aberrations can make designing these amplifiers difficult. One of the pioneers in high-bandwidth vertical amplifiers was the Tektronix company. Distributed amplifiers. These use transmission lines to temporarily split the signal and amplify each portion separately to achieve higher bandwidth than possible from a single amplifier. The outputs of each stage are combined in the output transmission line. This type of amplifier was commonly used on oscilloscopes as the final vertical amplifier. The transmission lines were often housed inside the display tube glass envelope. Switched mode amplifiers. These nonlinear amplifiers have much higher efficiencies than linear amps, and are used where the power saving justifies the extra complexity. Negative resistance devices. Negative resistances can be used as amplifiers, such as the tunnel diode amplifier. Microwave amplifiers. Traveling wave tube amplifiers. Traveling wave tube amplifiers are used for high-power amplification at low microwave frequencies. They typically can amplify across a broad spectrum of frequencies. However, They are usually not as tunable as klystrons. Klystrons. Klystrons are specialized linear beam vacuum devices, designed to provide high power, widely tunable amplification of millimeter and sub-millimeter waves. Klystrons are designed for large-scale operations, and despite having a narrower bandwidth than TWTAs, they have the advantage of coherently amplifying a reference signal so its output may be precisely controlled in amplitude, frequency and phase. Musical instrument amplifiers. An audio power amplifier is usually used to amplify signals such as music or speech. Several factors are especially important in the selection of musical instrument amplifiers and other audio amplifiers. Frequency response are not just the frequency range but the requirement that the signal level varies so little across the audible frequency range that the human ear notices no variation. A typical specification for audio amplifiers may be 20 Hz to 20 kHz +/0.5 dB. Power output the power level obtainable with little distortion, to obtain a sufficiently loud sound pressure level from the loudspeakers. Low distortion all amplifiers and transducers distort to some extent. They cannot be perfectly linear, but aim to pass signals without affecting the harmonic content of the sound more than the human ear can tolerate. That tolerance of distortion, and indeed the possibility that some warmth, or second harmonic distortion improves the musicality of the sound, are subjects of great debate. Classification of amplifier stages and systems. Many alternative classifications address different aspects of amplifier designs, and they all express some particular perspective relating the design parameters to the objectives of the circuit. Amplifier design is always a compromise of numerous factors, such as cost, power consumption, real-world device imperfections, and a multitude of performance specifications. Below are several different approaches to classification: input and output variables. Electronic amplifiers use one variable presented as either a current and voltage. Either current or voltage can be used as input and either as output, leading to 4 types of amplifiers. In idealized form they are represented by each of the 4 types of dependent source used in linear analysis, as shown in the figure, namely, each type of amplifier in its ideal form has an ideal input and output resistance that is the same as that of the corresponding dependent source. In practice the ideal impedances are only approximated. For any particular circuit, a small signal analysis is often used to find the impedance actually achieved. A small signal AC test current X is applied to the input or output node, all external sources are set to AC 0, and the corresponding alternating voltage Vx across the test current source determines the impedance seen at that node as R equals Vx/X. Amplifiers designed to attach to a transmission line at input and/or output, especially RF amplifiers, do not fit into this classification approach. Rather than dealing with voltage or current individually, they ideally couple with an input and/or output's impedance matched to the transmission line impedance, that is, match ratios of voltage to current. Many real RF amplifiers come close to this ideal. Although, for a given appropriate source and load impedance, RF amplifiers can be characterized as amplifying voltage or current, they fundamentally are amplifying power. Common terminal. One set of classifications for amplifiers is based on which device terminal is common to both the input and the output circuit. In the case of bipolar junction transistors, the 3 classes are common emitter, common base, and common collector. For field effect transistors, the corresponding configurations are common source, common gate, and common drain. For triode vacuum devices, common cathode, common grid, and common plate. The common emitter is most often configured to provide amplification of a voltage applied between base and emitter, and the output signal taken between collector and emitter will be inverted, relative to the input. The common collector arrangement applies the input voltage between base and collector, and to take the output voltage between emitter and collector. This results in negative feedback, and the output voltage will tend to follow the input voltage. The common collector circuit is therefore better known as an emitter follower, source follower, or cathode follower. Unilateral or bilateral. When an amplifier has an output that exhibits no feedback to its input side, it is called unilateral. The input's impedance of a unilateral amplifier is independent of the load, and the output's impedance is independent of the signal source impedance. If feedback connects part of the output back to the input of the amplifier, it is called a bilateral amplifier. The input's impedance of a bilateral amplifier is dependent upon the load, and the output's impedance is dependent upon the signal source impedance. All amplifiers are bilateral to some degree. However, they may often be modeled as unilateral under operating conditions where feedback is small enough to neglect for most purposes, simplifying analysis. Negative feedback is often applied deliberately to tailor amplifier behavior. Some feedback, which may be positive or negative, is unavoidable and often undesirable, introduced, for example, by parasitic elements such as the inherent capacitance between input and output of a device such as a transistor and capacitive coupling due to external wiring. Excessive frequency-dependent positive feedback may cause what is expected to be an amplifier to become an oscillator. Linear unilateral and bilateral amplifiers can be represented as two-port networks. Inverting or non-inverting. Another way to classify amplifiers is by the phase relationship of the input signal to the output signal. An inverting amplifier produces an output 180 degrees out of phase with the input signal. A non-inverting amplifier maintains the phase of the input signal waveforms. An emitter follower is a type of non-inverting amplifier, indicating that the signal at the emitter of a transistor is following the input signal. This description can apply to a single stage of an amplifier, or to a complete amplifier system. Function. Other amplifiers may be classified by their function or output characteristics. These functional descriptions usually apply to complete amplifier systems or subsystems and rarely to individual stages. A servo amplifier indicates an integrated feedback loop to actively control the output at some desired level. A DC servo indicates use at frequencies down to DC levels, where the rapid fluctuations of an audio or RF signal do not occur. These are often used in mechanical actuators, or devices such as DC motors that must maintain a constant speed or torque. An AC servo amp can do this for some AC motors. A linear amplifier responds to different frequency components independently, and does not generate harmonic distortion or intermodulation distortion. No amplifier can provide perfect linearity. A nonlinear amplifier generates significant distortion and so changes the harmonic content. There are situations where this is useful. Amplifier circuits intentionally providing a nonlinear transfer function include, a device like a silicon-controlled rectifier or a transistor used as a switch may be employed to turn either fully on or off a load such as a lamp based on a threshold in a continuously variable input. A nonlinear amplifier in an analog computer or true RMS converter, for example, can provide a special transfer function, such as logarithmic or square law. A Class C RF amplifier may be chosen because it can be very efficient, but will be nonlinear. Following such an amplifier with a tank-tuned circuit can reduce unwanted harmonics sufficiently to be useful in transmitters, or some desired harmonic may be selected by setting the resonant frequency of the tuned circuit to a higher frequency rather than fundamental frequency in frequency multiplier circuits. Automatic gain control circuits require an amplifier's gain be controlled by the time average amplitude so that the output amplitude varies little when weak stations are being received. The nonlinearities are assumed to be arranged so the relatively small signal amplitude suffers from little distortion yet is still modulated by the relatively large gain control DC voltage. AM detector circuits that use amplification such as anode bend detectors, precision rectifiers and infinite impedance detectors, as well as peak detector circuits, rely on changes in amplification based on the signal's instantaneous amplitude to derive a direct current from an alternating current input. Operational amplifier comparator and detector circuits. A wideband amplifier has a precise amplification factor over a wide frequency range, and is often used to boost signals for relay and communication systems. A narrow band amp amplifies a specific narrow range of frequencies, to the exclusion of other frequencies. An RF amplifier amplifies signals in the radio frequency range of the electromagnetic spectrum, and is often used to increase the sensitivity of a receiver or the output power of a transmitter. An audio amplifier amplifies audio frequencies. This category subdivides into small signal amplification, and power amps that are optimized to driving speakers, sometimes with multiple amps grouped together as separate or bridgeable channels to accommodate different audio reproduction requirements. Frequently used terms within audio amplifiers include preamplifier, which may include a phono preamp with or IAA equalization, or tape head preamps with CCIR equalization filters. They may include filters or tone control circuitry. Power amplifier, headphone amplifiers, and public address amplifiers. Stereo amplifiers imply two channels of output, though the term simply means solid sound. So quadraphonic stereo was used for amplifiers with 4 channels. 5.1 and 7.1 systems refer to home theater systems with 5 or 7 normal spatial channels, plus a subwoofer channel. Buffer amplifiers, which may include emitter followers, provide a high impedance input for a device that would otherwise draw too much current from the source. Line drivers are a type of buffer that feeds long or interference-prone interconnect cables, possibly with differential outputs through twisted pair cables. A special type of amplifier, originally used in analog computers, is widely used in measuring instruments for signal processing, and many other uses. These are called operational amplifiers or op-amps. The operational name is because this type of amplifier can be used in circuits that perform mathematical algorithmic functions, or operations on input signals to obtain specific types of output signals. Modern op-amps are usually provided as integrated circuits, rather than constructed from discrete components. A typical modern op-amp has differential inputs and one output. An idealized op-amp has the following characteristics: infinite inputs impedance, 0 outputs impedance, infinite gain, 0 propagation delay. The performance of an op-amp with these characteristics is entirely defined by the components that form a negative feedback loop around it. The amplifier itself does not affect the output. All real-world op-amps fall short of the idealized specification above, but some modern components have remarkable performance and come close in some respects. Interstage coupling method. Amplifiers are sometimes classified by the coupling method of the signal at the input, output, or between stages. Different types of these include resistive capacitive coupled amplifier, using a network of resistors and capacitors. By design, these amplifiers cannot amplify DC signals as the capacitors block the DC component of the input signal. RC-coupled amplifiers were used very often in circuits with vacuum tubes or discrete transistors. In the days of the integrated circuit, a few more transistors on a chip are much cheaper and smaller than a capacitor. Inductive capacitive coupled amplifier, using a network of inductors and capacitors. This kind of amplifier is most often used in selective radio frequency circuits. Transformer-coupled amplifier, using a transformer to match impedances or to decouple parts of the circuits. Quite often LC-coupled and transformer-coupled amplifiers cannot be distinguished as a transformer as some kind of inductor. Direct-coupled amplifier, using no impedance and bias matching components. This class of amplifier was very uncommon in the vacuum tube days when the anode voltage was at greater than several hundred volts and the grid voltage at a few volts minus. So they were only used if the gain was specified down to DC. In the context of modern electronics, developers are encouraged to use directly coupled amplifiers whenever possible. Frequency range. Depending on the frequency range and other properties, amplifiers are designed according to different principles. Frequency ranges down to DC are only used when this property is needed. DC amplification leads to specific complications that are avoided if possible. DC blocking capacitors are added to remove DC and subsonic frequencies from audio amplifiers. Depending on the frequency range specified, different design principles must be used. Up to the megahertz range, only discrete properties need be considered. For example, a terminal has an input impedance. As soon as any connection within the circuit gets longer than perhaps 1% of the wavelength of the highest specified frequency, design properties radically change. For example, A specified length and width of a PCB trace can be used as a selective or impedance matching entity. Above a few hundred megahertz, it gets difficult to use discrete elements, especially inductors. In most cases, PCB traces of very closely defined shapes are used instead. The frequency range handled by an amplifier might be specified in terms of bandwidth, or by specifying a frequency response that is within a certain number of decibels between a lower and an upper frequency. Power amplifier classes. Power amplifier circuits are classified as A, B and C for analog designs, and Class D and E for switching designs based on the proportion of each input cycle, during which an amplifying device is passing current. The image of the conduction angle is derived from amplifying a sinusoidal signal. If the device is always on, the conducting angle is 360 degrees. If it is on for only half of each cycle, the angle is 180 degrees. The angle of flow is closely related to the amplifier power efficiency. The various classes are introduced below, followed by a more detailed discussion under their individual headings further down. In the illustrations below, a bipolar junction transistor is shown as the amplifying device, but the same attributes are found if with MOSFETs or vacuum tubes. Conduction angle classes. Class A, 100% of the input signal is used. The active element remains conducting all of the time. Class B, 50% of the input signal is used. The active element carries current half of each cycle, and is turned off for the other half. Class AB. Class AB is intermediate between Class A and B. The two active elements conduct more than half of the time. Class C, less than 50% of the input signal is used. A Class D amplifier uses some form of pulse width modulation to control the output devices. The conduction angle of each device is no longer related directly to the input signal but instead varies in pulse width. These are sometimes called digital amplifiers because the output device is switched fully on or off, and not carrying current proportional to the signal amplitude. Additional classes. There are several other amplifier classes, although they are mainly variations of the previous classes. For example, Class G and Class H amplifiers are marked by variation of the supply rails following the input signal. Wasted heat on the output devices can be reduced as excess voltage is kept to a minimum. The amplifier that is fed with these rails itself can be of any class. These kinds of amplifiers are more complex, and are mainly used for specialized applications, such as very high power units. Also, Class E and Class F amplifiers are commonly described in literature for radio frequency applications where efficiency of the traditional classes is important, yet several aspects deviate substantially from their ideal values. These classes use harmonic tuning of their output networks to achieve higher efficiency and can be considered a subset of Class C due to their conduction angle characteristics. Class A amplifying devices operating in Class A conduct over the entire range of the input cycle. A Class A amplifier is distinguished by the output stage devices being biased for Class A operation. Subclass A-Do is sometimes used to refer to vacuum tube Class A stages where the grid is allowed to be driven slightly positive on signal peaks, resulting in slightly more power than normal Class A, but this incurs a higher distortion level. Advantages of Class A amplifiers. Class A designs are simpler than other classes. For example, Class A, B and B designs require two connected devices in the circuit, each to handle one half of the waveform. Class A can use a single device. The amplifying element is biased so the device is always conducting, the quiescent collector current is close to the most linear portion of its transconductance curve. Because the device is never off, there is no turn-on time, no problems with charge storage, and generally better high-frequency performance and feedback loop stability. The point at which the device comes closest to being off is not at zero signal, so the problems of crossover distortion associated with Class A, B and B designs is avoided. Disadvantage of Class A amplifiers. Class A amplifiers are inefficient. A theoretical efficiency of 50% is obtainable with transformer output coupling and only 25% with capacitive coupling, unless deliberate use of nonlinearities is made. In a power amplifier, this not only wastes power and limits operation with batteries, but increases operating costs and requires higher rated output devices. Inefficiency comes from the standing current that must be roughly half the maximum output current, and a large part of the power supply voltage is present across the output device at low signal levels. If high output power is needed from a Class A circuit, the power supply and accompanying heat becomes significant. For every watt delivered to the load, the amplifier itself, at best, uses an extra watt. For high-power amplifiers this means very large and expensive power supplies and heat sinks. Class A power amplifier designs have largely been superseded by more efficient designs, though they remain popular with some hobbyists, mostly for their simplicity. There is a market for expensive high-fidelity Class A amps considered a cult item amongst audiophiles mainly for their absence of crossover distortion and reduced odd harmonic and high-order harmonic distortion. Single-ended and triode Class A amplifiers. Some hobbyists who prefer Class A amplifiers also prefer the use of thermionic valve designs instead of transistors, for several reasons. Single-ended output stages have an asymmetrical transfer function, meaning that even-order harmonics in the created distortion tend not to be cancelled. For tubes, or FETs, most of the distortion is second-order harmonics, from the square law transfer characteristic, which to some produces a warmer, and more pleasant sound. For those who prefer low distortion figures, the use of tubes with Class A together with symmetrical circuits results in the cancellation of most of the even distortion harmonics, hence the removal of most of the distortion. Historically, valve amplifiers often used a Class A power amplifier simply because valves are large and expensive. Many Class A designs use only a single device. Transistors are much cheaper, and so more elaborate designs that give greater efficiency but use more parts are still cost-effective. A classic application for a pair of Class A devices is the long-tailed pair, which is exceptionally linear, and forms the basis of many more complex circuits, including many audio amplifiers and almost all op-amps. Class A amplifiers are often used in output stages of high-quality op-amps. They are sometimes used as medium power, low efficiency, and high-cost audio power amplifiers. The power consumption is unrelated to the output power. At idle, the power consumption is essentially the same as at high output volume. The result is low efficiency and high heat dissipation. Class B. Class B amplifiers only amplify half of the input wave cycle, thus creating a large amount of distortion, but their efficiency is greatly improved and is much better than Class A. Class B amplifiers are also favored in battery-operated devices, such as transistor radios. Class B has a maximum theoretical efficiency of I/4. This is because the amplifying element is switched off altogether half of the time, and so cannot dissipate power. A single Class B element is rarely found in practice, though it has been used for driving the loudspeaker in the early IBM personal computers with beeps, and it can be used in a Ef power amplifier where the distortion levels are less important. However, Class C is more commonly used for this. A practical circuit using Class B elements is the pusher-pull stage, such as the very simplified complementary pair arrangement shown below. Here, complementary or quasi-complementary devices are each used for amplifying the opposite halves of the input signal, which is then recombined at the output. This arrangement gives excellent efficiency, but can suffer from the drawback that there is a small mismatch in the crossover region at the joins between the two halves of the signal, as one output device has to take over supplying power exactly as the other finishes. This is called crossover distortion. An improvement is to bias the devices so they are not completely off when they're not in use. This approach is called Class AB operation. Class AB is widely considered a good compromise for amplifiers, since much of the time the music signal is quiet enough that the signal stays in the Class A region, where it is amplified with good fidelity, and by definition if passing out of this region, is large enough that the distortion products typical of Class B are relatively small. The crossover distortion can be reduced further by using negative feedback. In Class AB operation, each device operates the same way as in Class B over half the waveform, but also conducts a small amount on the other half. As a result, the region where both devices simultaneously are nearly off is reduced. The result is that when the waveforms from the two devices are combined, the crossover is greatly minimized or eliminated altogether. The exact choice of quiescent current, the standing current through both devices when there is no signal, makes a large difference to the level of distortion. Often the bias voltage applied to set this quiescent current has to be adjusted with the temperature of the output transistors. Another approach is to include small-value resistors in series with the emitters. Class AB sacrifices some efficiency over Class B in favor of linearity, thus is less efficient. It is typically much more efficient than Class A. Sometimes a numeral is added for vacuum tube stages. If the grid voltage is always negative with respect to the cathode, the class is AB1. If the grid is allowed to go slightly positive on signal peaks, the class is AB2. Class C. Class C amplifiers conduct less than 50% of the input signal and the distortion at the output is high, but high efficiencies are possible. The usual application for Class C amplifiers is in RF transmitters operating at a single fixed carrier frequency, where the distortion is controlled by a tuned load on the amplifier. The input signal is used to switch the active device, causing pulses of current to flow through a tuned circuit forming part of the load. The Class C amplifier has two modes of operation, tuned and untuned. The diagram shows a waveform from a simple Class C circuit without the tuned load. This is called untuned operation, and the analysis of the waveforms shows the massive distortion that appears in the signal. When the proper load is used, two things happen. The first is that the output's bias level is clamped with the average output voltage equal to the supply voltage. This is why tuned operation is sometimes called a clamper. This allows the waveform to be restored to its proper shape despite the amplifier having only a one-polarity supply. This is directly related to the second phenomenon: the waveform on the center frequency becomes less distorted. The residual distortion is dependent upon the bandwidth of the tuned load, with the center frequency seeing very little distortion, but greater attenuation the farther from the tuned frequency that the signal gets. The tuned circuit resonates at one frequency, the fixed carrier frequency, and so the unwanted frequencies are suppressed, and the wanted full signal is extracted by the tuned load. The signal bandwidth of the amplifier is limited by the Q factor of the tuned circuit, but this is not a serious limitation. Any residual harmonics can be removed using a further filter. In practical Class C amplifiers, a tuned load is invariably used. In one common arrangement, the resistor shown in the circuit above is replaced with a parallel tuned circuit consisting of an inductor and capacitor in parallel, whose components are chosen to resonate the frequency of the input signal. Power can be coupled to a load by transformer action with a secondary coil wound on the inductor. The average voltage at the drain is then equal to the supply voltage, and the signal voltage appearing across the tuned circuit varies from near zero to near twice the supply voltage during the Ef cycle. The input circuit is biased so that the active element conducts for only a fraction of the Ef cycle, usually 1/3 or less. The active element conducts only while the drain voltage is passing through its minimum. By this means, power dissipation in the active device is minimized, and efficiency increased. Ideally, the active element would pass only an instantaneous current pulse while the voltage across it is zero. It then dissipates no power and 100% efficiency is achieved. However, practical devices have a limit to the peak current they can pass, and the pulse must therefore be widened to around 120 degrees, to obtain a reasonable amount of power, and the efficiency is then 60 to 70%. Class D. In the Class D amplifier, the active devices function as electronic switches instead of linear gain devices. They are either on or off. The analog signal is converted to a stream of pulses that represents the signal by pulse width modulation, pulse density modulation, delta sigma modulation or a related modulation technique before being applied to the amplifier. The time average power value of the pulses is directly proportional to the analog signal, so after amplification the signal can be converted back to an analog signal by a passive low-pass filter. The purpose of the output filter is to smooth the pulse stream to an analog signal, removing the high-frequency digital spectral components. The frequency of the output pulses is typically 10 or more times the highest frequency in the input signal to be amplified, so that the filter can adequately reduce the digital components, producing an accurate reproduction of the input. The main advantage of a Class D amplifier is power efficiency. Because the output pulses have a fixed amplitude, the switching elements in bipolar transistors were once used, are switched either completely on or completely off, rather than operated in linear mode. A MOSFET operates with the lowest resistance when fully on and thus has the lowest power dissipation when in that condition. Compared to an equivalent Class AB device, a Class D amplifier's lower losses permit the use of a smaller heatsink for the MOSFETs while also reducing the amount of input power required, allowing for a lower capacity power supply design. Therefore, Class D amplifiers are typically smaller than an equivalent Class AB amplifier. Another advantage of the Class D amplifier is that it can operate from a digital signal source without requiring a digital to analog converter to convert the signal to analog form first. If the signal source is in digital form, such as in a digital media player or computer sound card, the digital circuitry can convert the binary digital signal directly to a pulse width modulation signal to be applied to the amplifier, simplifying the circuitry considerably. Class D amplifiers have been widely used to control motors, but they are now also used as power amplifiers, with some extra circuitry to allow analog to be converted to a much higher frequency pulse width modulated signal. Switching power supplies have even been modified into crude Class D amplifiers. High-quality Class D audio power amplifiers have now appeared on the market. These designs have been said to rival traditional AB amplifiers in terms of quality. An early use of Class D amplifiers was high-power subwoofer amplifiers in cars. Because subwoofers are generally limited to a bandwidth of no higher than 150 Hz, the switching speed for the amplifier does not have to be as high as for a full-range amplifier, allowing simpler designs. Class D amplifiers for driving subwoofers are relatively inexpensive in comparison to Class AB amplifiers. The letter D used to designate this amplifier class is simply the next letter after C and, although occasionally used as such, does not stand for digital. Class D and Class E amplifiers are sometimes mistakenly described as digital, because the output waveform superficially resembles a pulse train of digital symbols, but a Class D amplifier merely converts an input waveform into a continuously pulse-width modulated analog signal. Additional classes: Class E. The Class Ef amplifier is a highly efficient switching power amplifier, typically used at such high frequencies that the switching time becomes comparable to the duty time. As said in the Class D amplifier, the transistor is connected via a serial LC circuit to the load, and connected via a large L to the supply voltage. The supply voltage is connected to ground via a large capacitor to prevent any RF signals leaking into the supply. The Class E amplifier adds a C between the transistor and ground and uses a defined L1 to connect to the supply voltage. The following description ignores DC, which can be added easily afterwards. The above-mentioned C and L are in effect a parallel LC circuit to ground. When the transistor is on, it pushes through the serial LC circuit into the load and some current begins to flow to the parallel LC circuit to ground. Then the serial LC circuit swings back and compensates the current into the parallel LC circuit. At this point the current through the transistor is zero and it is switched off. Both LC circuits are now filled with energy in C and LO. The whole circuit performs a damped oscillation. The damping by the load has been adjusted so that sometime later the energy from the LS is gone into the load, but the energy in both CO peaks at the original value to in turn restore the original voltage so that the voltage across the transistor is zero again and it can be switched on. With load, frequency, and duty cycle as given parameters and the constraint that the voltage is not only restored, but peaks at the original voltage, the four parameters are determined. The Class E amplifier takes the finite on resistance into account and tries to make the current touch the bottom at zero. This means that the voltage and the current at the transistor are symmetric with respect to time. The Fourier transform allows an elegant formulation to generate the complicated LC networks and says that the first harmonic is passed in the load, all even harmonics are shorted and all higher odd harmonics are open. Class E uses a significant amount of second harmonic voltage. The second harmonic can be used to reduce the overlap with edges with finite sharpness. For this to work, energy on the second harmonic has to flow from the load into the transistor, and no source for this is visible in the circuit diagram. In reality, the impedance is mostly reactive and the only reason for it is that Class E is a Class F amplifier with a much simplified load network and thus has to deal with imperfections. In many amateur simulations of Class E amplifiers, sharp current edges are assumed, nullifying the very motivation for Class E, and measurements near the transit frequency of the transistors show very symmetric curves, which look much similar to Class F simulations. The Class E amplifier was invented in 1972 by Nathan O. Sokol and Alan D. Sokol, and details were first published in 1975. Some earlier reports on this operating class have been published in Russian. Class F, in pusher-pull amplifiers and in CMOS, the even harmonics of both transistors just cancel. Experiment shows that a square wave can be generated by those amplifiers. Theoretically, square waves consist of odd harmonics only. In a Class D amplifier, the output filter blocks all harmonics. That is, the harmonics see an open load. So even small currents in the harmonics suffice to generate a voltage square wave. The current is in phase with the voltage applied to the filter, but the voltage across the transistors is out of phase. Therefore, there is a minimal overlap between current through the transistors and voltage across the transistors. The sharper the edges, the lower the overlap. While in Class D, transistors and the load exist as two separate modules, Class F admits imperfections like the parasitics of the transistor and tries to optimize the global system to have a high impedance at the harmonics. Of course, there has to be a finite voltage across the transistor to push the current across the on-state resistance. Because the combined current through both transistors is mostly in the first harmonic, it looks like a sine. That means that in the middle of the square the maximum of current is to flow, so it may make sense to have a dip in the square, or in other words to allow some overswing of the voltage square wave. A Class F load network by definition has to transmit below a cutoff frequency and reflect above. Any frequency lying below the cutoff and having its second harmonic above the cutoff can be amplified, that is an octave bandwidth. On the other hand, an inductive capacitive series circuit with a large inductance and a tunable capacitance may be simpler to implement. By reducing the duty cycle below 0.5, the output amplitude can be modulated. The voltage square waveform degrades, but any overheating is compensated by the lower overall power flowing. Any load mismatch behind the filter can only act on the first harmonic current waveform. Clearly only a purely resistive load makes sense, then the lower the resistance, the higher the current. Class F can be driven by sine or by a square wave. For a sine the input can be tuned by an inductor to increase gain. If Class F is implemented with a single transistor, the filter is complicated to short the even harmonics. All previous designs use sharp edges to minimize the overlap. Classes G and H. There are a variety of amplifier designs that enhance Class AB output stages with more efficient techniques to achieve greater efficiencies with low distortion. These designs are common in large audio amplifiers since the heat sinks and power transformers would be prohibitively large without the efficiency increases. The terms Class G and Class H are used interchangeably to refer to different designs, varying in definition from one manufacturer or paper to another. Class G amplifiers are more efficient than Class AB amplifiers. These amplifiers provide several power rails at different voltages and switch between them as the signal output approaches each level. Thus, the amplifier increases efficiency by reducing the wasted power at the output transistors. Class G amplifiers are more efficient than Class AB but less efficient when compared to Class D, however, they do not have the electromagnetic interference effects of Class D. Class H amplifiers take the idea of Class G one step further, creating an infinitely variable supply rail. This is done by modulating the supply rails so that the rails are only a few volts larger than the output signal at any given time. The output stage operates at its maximum efficiency all the time. Switched-mode power supplies can be used to create the tracking rails. Significant efficiency gains can be achieved but with the drawback of more complicated supply design and reduced THD performance. In common designs, a voltage drop of about 10 V is maintained over the output transistors in Class H circuits. The picture above shows positive supply voltage of the output stage and the voltage at the speaker output. The boost of the supply voltage is shown for a real music signal. The voltage signal shown is thus a larger version of the input, but has been changed in sign by the amplification. Other arrangements of amplifying device are possible, but that given is the easiest to understand and employ in practice. If the amplifying element is linear, the output is a faithful copy of the input, only larger and inverted. In practice, transistors are not linear, and the output only approximates the input. Nonlinearity from any of several sources is the origin of distortion within an amplifier. The class of amplifier depends on how the amplifying device is biased. The diagrams omit the bias circuits for clarity. Any real amplifier is an imperfect realization of an ideal amplifier. An important limitation of a real amplifier is that the output it generates is ultimately limited by the power available from the power supply. An amplifier saturates and clips the output if the input signal becomes too large for the amplifier to reproduce or exceeds operational limits for the device. Dirty amplifiers. The dirty, a hybrid configuration, is currently receiving renewed attention. It was invented in 1934 by William H. Doherty for Bell Laboratories Euro, whose sister company, Western Electric, manufactured radio transmitters. The dirty amplifier consists of a Class B primary or carrier stages in parallel with a Class C auxiliary or peak stage. The input signal splits to drive the two amplifiers, and a combining network sums the two output signals. Phase-shifting networks are used in inputs and outputs. During periods of low signal level, the Class B amplifier efficiently operates on the signal and the Class C amplifier is cut off and consumes little power. During periods of high signal level, the Class B amplifier delivers its maximum power and the Class C amplifier delivers up to its maximum power. The efficiency of previous AM transmitter designs was proportional to modulation but, with average modulation typically around 20%, transmitters were limited to less than 50% efficiency. In Doherty's design, even with zero modulation, a transmitter could achieve at least 60% efficiency. As a successor to Western Electric for broadcast transmitters, the Doherty concept was considerably refined by Continental Electronics Manufacturing Company of Dallas, TX. Perhaps, the ultimate refinement was the screen grid modulation scheme invented by Joseph B. Sainton. The Sainton amplifier consists of a Class C primary or carrier stage in parallel with a Class C auxiliary or peak stage. The stages are split and combined through 90-degree phase-shifting networks as in the Doherty amplifier. The unmodulated radio frequency carrier is applied to the control grids of both tubes. Carrier modulation is applied to the screen grids of both tubes. The bias point of the carrier and peak tubes is different, and is established such that the peak tube is cut off when modulation is absent whereas both tubes contribute twice the rated carrier power during 100% modulation. As both tubes operate in Class C, a significant improvement in efficiency is thereby achieved in the final stage. In addition, as the tetrode carrier and peak tubes require very little drive power, a significant improvement in efficiency within the driver stage is achieved as well. The released version of the Sainton amplifier employs a cathode follower modulator, not a pusher-pull modulator. Previous Continental Electronics designs, by James O. Weldon and others, retained most of the characteristics of the Doherty amplifier but added screen grid modulation of the driver. The Doherty amplifier remains in use in very high-power AM transmitters, but for lower-power AM transmitters, vacuum tube amplifiers in general were eclipsed in the 1980s by arrays of solid-state amplifiers, which could be switched on and off with much finer granularity in response to the requirements of the input audio. However, interest in the dirty configuration has been revived by cellular telephone and wireless Internet applications where the sum of several constant envelope users creates an aggregate AM result. The main challenge of the dirty amplifier for digital transmission modes is in aligning the two stages and getting the Class C amplifier to turn on and off very quickly. Recently, dirty amplifiers have found widespread use in cellular base station transmitters for GHz frequencies. Implementations for transmitters in mobile devices have also been demonstrated. Implementation: amplifiers are implemented using active elements of different kinds. The first active elements were relays. They were for example used in transcontinental telegraph lines. A weak current was used to switch the voltage of a battery to the outgoing line. For transmitting audio, carbon microphones were used as the active element. This was used to modulate a radio frequency source in one of the first AM audio transmissions, by Reginald Fessenden on December 24, 1906. Amplifiers used vacuum tubes exclusively until the 1960s. Today, tubes are used for specialist audio applications such as guitar amplifiers and audiophile amplifiers. Many broadcast transmitters still use vacuum tubes. In the 1960s, the transistor started to take over. These days, discrete transistors are still used in high-power amplifiers and in specialist audio devices. Beginning in the 1970s, more and more transistors were connected on a single chip, therefore creating the integrated circuit. A large number of amplifiers commercially available today are based on integrated circuits. For special purposes, other active elements have been used. For example, in the early days of the satellite communication, parametric amplifiers were used. The core circuit was a diode whose capacity was changed by an RF signal created locally. Under certain conditions, this RF signal provided energy that was modulated by the extremely weak satellite signal received at the Earth station. Amplifier Circuit. The practical amplifier circuit to the right could be the basis for a moderate power audio amplifier. It features a typical design as found in modern amplifiers, with a Class AB pusher/pull output stage, and uses some overall negative feedback. Bipolar transistors are shown, but this design would also be realizable with FETs or valves. The input signal is coupled through capacitor C1 to the base of transistor Q1. The capacitor allows the AC signal to pass, but blocks the DC bias voltage established by resistors R1 and R2 so that any preceding circuit is not affected by it. Q1 and Q2 form a differential amplifier, in an arrangement known as a long-tailed pair. This arrangement is used to conveniently allow the use of negative feedback, which is fed from the output to Q2 via R7 and R8. The negative feedback into the difference amplifier allows the amplifier to compare the input to the actual output. The amplified signal from Q1 is directly fed to the second stage, Q3, which is a common emitter stage that provides further amplification of the signal and the DC bias for the output stages, Q4 and Q5. R6 provides the load for Q3. So far, all of the amplifier is operating in Class A. The output pair are arranged in Class AB pusher/pull, also called a complementary pair. They provide the majority of the current amplification and directly drive the load, connected via DC blocking capacitor C2. The diodes D1 and D2 provide a small amount of constant voltage bias for the output pair, just biasing them into the conducting state so that crossover distortion is minimized. That is, the diodes push the output stage firmly into Class AB mode. This design is simple, but a good basis for a practical design because it automatically stabilizes its operating point, since feedback internally operates from DC up through the audio range and beyond. Further circuit elements would probably be found in a real design that would roll off the frequency response above the needed range to prevent the possibility of unwanted oscillation. Also, the use of fixed diode bias as shown here can cause problems if the diodes are not both electrically and thermally matched to the output transistor. If the output transistors turn on too much, they can easily overheat and destroy themselves, as the full current from the power supply is not limited at this stage. A common solution to help stabilize the output devices is to include some emitter resistors, typically an ohm or so. Calculating the values of the circuit's resistors and capacitors is done based on the components employed and the intended use of the amp. For the basics of radio frequency amplifiers using valves, see valved RF amplifiers. Notes on implementation: real-world amplifiers are imperfect. One consequence is that the power supply itself may influence the output, and must itself be considered when designing the amplifier. A power amplifier is effectively an input signal-controlled power regulator, regulating the power sourced from the power supply or mains to the amplifier's load. The power output from a power amplifier cannot exceed the power input to it. The amplifier circuit has an open-loop performance that can be described by various parameters. Many modern amplifiers use negative feedback techniques to hold the gain at the desired value and to reduce distortion. Negative loop feedback has the intended effect of electrically damping loudspeaker motion, thereby damping the mechanical dynamic performance of the loudspeaker. When assessing rated amplifier power output, it is useful to consider the load to be applied, the form of signal, that is speech or music, duration of power output needed, for example short time or continuous, and dynamic range required, for example recorded program or live. In the case of high-powered audio applications requiring long cables to the load, for example cinemas and shipping centers, instead of using heavy-gauge cables it may be more efficient to connect to the load at line output voltage with matching transformers at source and loads. To prevent instability and/or overheating, care is needed to ensure solid-state amplifiers are adequately loaded. Most have a rated minimum load impedance. All amplifiers generate heat through electrical losses. This heat must be dissipated via natural or forced air cooling. Heat can damage or reduce service life of electronic components. Consideration should be given to the heating effects of or upon adjacent equipment. Different methods of supplying power result in many different methods of bias. Bias is a technique by which the active devices are set up to operate in a particular region, or by which the DC component of the output signal is set to the midpoint between the maximum voltages available from the power supply. Most amplifiers use several devices at each stage. They are typically matched in specifications except for polarity. Matched inverted polarity devices are called complementary pairs. Class A amplifiers generally use only one device, unless the power supply is set to provide both positive and negative voltages, in which case a dual-device symmetrical design may be used. Class C amplifiers, by definition, use a single polarity supply. Amplifiers often have multiple stages and cascade to increase gain. Each stage of these designs may be a different type of amp to suit the needs of that stage. For instance, the first stage might be a Class A stage, feeding a Class AB pusher/pull second stage, which then drives a Class G final output stage, taking advantage of the strengths of each type, while minimizing their weaknesses. See also. References. External links: Rain Audio's Guide to Amplifier Classes, Design and Analysis of a Basic Class D Amplifier, Conversion, Distortion Factor to Distortion Attenuation and THD, an alternate topology called the Grounded Bridge Amplifier, PDF, contains an explanation of different amplifier classes, PDF. Reinventing the Power Amplifier, PDF, Anatomy of the Power Amplifier, including information about classes, tons of tones, site explaining nonlinear distortion stages and amplifier models, Class D audio amplifiers, white paper, PDF, Class E radio transmitters, tutorials, schematics, examples, and construction details.